Can you stretch space? Let's go. In our last video, we saw that Euclidean or planar geometry gave us the Pythagorean theorem, a way of measuring distances in the plane, and especially in the coordinate plane. Now, another feature on the plane is that triangles drawn in the plane, all three of the angles inside of them always add up to 180 degrees. But that's actually not true on the surface of the Earth. It's curved, and that changes things. Curved surfaces actually have a lot of different properties than flat surfaces, and so we're going to talk about some of those differences. Here's a quick overview. Parametric equations for curves can be described as vectors. Tangent and normal vectors lay the framework for measuring spatial length and direction. And one more thing about right triangles. You see, trigonometry provides a connection between measuring lengths and direction angles in the plane. Sine, cosine, and tangent are used in many branches of mathematics. Parametric curves, defined by a variable called the parameter, trace out a path through space. At any point along that curve, we can define a tangent vector by taking the derivative of that parametric curve. Tangent vectors and tangent lines describe how objects move along such curves. The magnitude of the tangent vector is a key component in defining arc length, sometimes defined by the variable s. A unit tangent vector can also be defined in the natural way. The length of the tangent vector can be integrated over the curve to get a total arc length, and the second derivative can define acceleration to that curve, something that has to do with spatial curvature. The magnitude of the acceleration vector defines the curvature of a path. So, if we were to measure the curvature, it would be the same thing as measuring the force needed to stay on a path. Around a circle, the acceleration vector's length does not change. Curvature measures the force needed to stay on a path. If the radius of the circle began to shrink, the curvature would increase. There's an inversely proportional relationship between the two. More curvature, smaller radius. Larger radius, less curvature. Let me say that again. If we started to shrink the radius of the circle, then we should see an increase in the curvature. The relationship is that the curvature varies inversely with the radius. Curves on three-dimensional surfaces such as a sphere will introduce more dimensions to consider, and thus surface curvature depends on direction. Let's figure out parametric surfaces for a moment. So surfaces in three dimensions start with picking a domain in the xy plane. And that domain is going to be mapped into a third dimension, a z direction, to create a surface. So the z direction is described by a function given in both terms of x and y. And we can also describe this, of course, with vectors, but given a domain in the xy plane, we can use it or describe a parametric surface in three dimensions, and we can use vector notation to describe that. So in general, let's say we have a UV parameter plane. That is, we have two parameters for a surface and we pick a domain in that surface. We are going to map that into 3 dimensions by some function. A function that takes a 2-dimensional plane to a 3-dimensional surface. So it embeds it in a 3-dimensional space. So the more dimensions we have, the more parameters we need, and the more complex the space becomes. Let's consider the surface of a can or a cylinder. It is curved in one direction, positively, and straight or flat in the other direction. In the red direction, it's a straight line, it's flat. In the green direction, it's curved. So there are 2 principal directions and 2 principal curvatures we can define along the surface of that cylinder. The product of these things is called the Gaussian or surface curvature for that object. Since in the red direction it's flat or has 0 curvature, and in the green direction it has the curvature of a circle, 1 over its radius, we ultimately get a product that is 0. This just means if we lived on the surface of the cylinder, it would seem flat to us, just like living on the surface of the Earth does. Spheres have the same curvature in all directions. The principal curvatures being both 1 over the radius, we get a total surface curvature as 1 over the radius squared. However, a hyperbolic surface has different signed curvatures in the principal directions, leading an overall negative Gaussian curvature. Carl Friedrich Gauss, one of the greatest mathematicians of the 19th century, spent 10 years of his adult life doing geodetic surveying and inventing differential geometry, the means by which to investigate these landscapes. In calculus, we study curves and, more importantly, the tangent line to the curve, a line that touches the curve in just one spot, and whose slope informs us about how fast the curve is actually changing. Gauss realized tangent planes could provide the linear transformations to describe how surfaces curve. This is done through a function called the Gauss map, or normal vector mapping, and it takes tangent planes of surfaces to compare them to tangent planes of the unit sphere. He observed that there's a 1-to-1 correspondence that exists under the tangent plane map that sold him on the idea that curvature of surfaces could be deeply analyzed through these conditions. The Gauss map sends a unit normal vector on the surface to a unit radial position vector in the unit sphere. Differentiating this map gives us the connection between the tangent planes. The Gauss map works like this. Take a surface S that is embedded into 3 dimensions, parameterize a curve on that surface. At any point, define a set of tangent vectors, which can be defined along the 2 parameter directions, the principal directions. The tangent vectors provide a set of basis vectors for the tangent plane or tangent space, and it also gives us a way of defining a unit normal vector that will be perpendicular to that tangent plane. These tangent basis vectors along with the normal vector provide a set of basis vectors for the moving framework along the curve, and also gives us a way of defining surface area through double integration along the surface. So normal vectors to tangent planes and the radial position vector of a unit sphere both have the same tangent plane. So differential geometry is simply just the calculus of geometric objects like surfaces. Alright, so let's discuss differential geometry so far. We take a parametric plane described by the parameters uv and map it into the 3rd dimension z with a mapping that describes z in terms of x and y. And we can describe curves on the surface of that mapping as a parametric curve on a parametric surface, and we can define the length of that curve, or the arc length, by integrating the length of the tangent vector along that curve. Measuring lengths and distances along a surface living in 3 dimensions or higher makes use of a tool called the metric tensor, a matrix of numbers that represents something called the first fundamental form, or the metric form. Partial derivatives of the curve with respect to the parameters are the tangent basis vectors. Since the multivariable chain rule is used to differentiate the curve, we see it as a linear combination of basis vectors and components. The 2x2 metric tensor matrix contains the coefficients obtained by the dot product of these basis vectors. The dot product of these basis vectors, these tangent vectors, form completely an idea of what arc length is along these parametric curves. By examining these dot products, we find that the metric tensor is symmetric. So the squared magnitude of the tangent vector is the quadratic first fundamental form. Okay, let's start with a point, which is 0-dimensional. If you move that point in 1 dimension, we get a line. Now take that line and move it in a different dimension, and you're going to get a plane. Now what happens if you take a plane and move it in a new dimension? You then get a prism, or a 3-dimensional object, which you're probably familiar with. However, if we start continuing this process, what happens if we move a 3-dimensional object in the next dimension? Well, when we start moving into higher dimensions, we work with manifolds. At any point on a surface in 3-dimensional space, we can define a unit normal vector perpendicular to the tangent plane. That unit normal is exactly equivalent to a unit normal to the radial vector at a point on the surface of the 2-sphere, or sphere in 3-dimensional space. So the Gauss map differentiated gives the map between tangent spaces, or tangent planes, for which a 1-to-1 correspondence exists, which in the language of linear algebra is a linear transformation, a requirement for parallelism and the foundation of any good geometry. Next, we're going to have to talk about the Riemann curvature tensor, created by Bernard Riemann, a mathematician who is also a student of Gauss. Manifolds are n-dimensional spaces. Tensors are the tools we use to analyze these n-dimensional spaces. The shortest path between 2 points in space is called a geodesic. And recall that surface or Gaussian curvature can either be positive, negative, or flat, which would be zero curvature.
Imagine that. It never occurred to me to think of space as the thing that was moving.
Because of the limitations of Gaussian curvature in 2 dimensions, the Riemann curvature tensor uses a process called parallel transport, in which a test vector is transported around a closed loop formed by 2 input vectors. A gap detected in this loop is a measure of the curvature in the space. And through this process, we develop a unique connection between basis vectors and their components. The Levi-Civita connection, or the covariant derivative, expressed through the Christoffel symbols, gives us this unique connection.
Wow, you can really dance. Wow, you can really dance. He went he went. They said we've both been dancing all this time. What a coincidence!
A quick peek into tensor calculus, just a little bit. The Riemann tensor has component values from each input, VW and T, acting on the basis vector E alpha. Components are calculated through the covariant derivative using the del operator, and the Christoffel gamma symbols are the affine connection coefficients that define the difference between extrinsic and intrinsic geometry. The Ricci tensor, that measures the trace of the Riemann tensor, is a true measure of the curvature of a manifold, something Einstein would take advantage of. So the Riemann tensor can measure something called geodesic deviation, or how spread apart geodesics move from each other. Einstein makes a very physical connection. What is gravity? The Einstein field equations connect the curvature of space through the Ricci tensor, the metric tensor, and some other things there, and something called the stress energy momentum tensor. That connects the energy or mass value to how space is actually stretched or warped in its presence. Matter warps space, and space tells matter how to move. Not long after Einstein published his results, a guy by the name of Schwarzschild came along and found a very unique solution to his equations. Using spherical symmetries, Schwarzschild realized that if matter were condensed into a spherical radius, the Schwarzschild radius, it would cause a black hole, a place where space stretches faster than light. Not even light can escape it. Einstein's theory of relativity showed an intimate connection between space and time. So space-time metrics are often used when finding a distance between two events. In a black hole, once you've crossed the event horizon, the point of no return, space and time become inverted. You can only move in one spatial direction, but time seems to flow in multi-directions. Space-time becomes time-space. And for that reason, I'm out of here. Hey, thanks for watching. Please hit that like, subscribe, and notification bell for more videos. Stay tuned.